Yeah. Um, Welcome, everyone. So I would like to start by saying that it is kind of a miracle that every year around this time, I'm invited to give a lecture to the department. So this is what happened in the previous 3 years. And my first lecture is on, February 21st, 2020, that I gave a lecture on brief history of fluid mechanics. And the only exception is for the second one, which is during COVID. So it's kind of messed up. That is after half a year of the first one. And then last year at this time, I'm again invited to give a lecture to represent the brief history of fluid mechanics. And then this year again. And what makes this more special is that this time is actually around my birthday, which is February 21st. So thank you very much for the birthday gift to inviting me again this year.
29 again?
Yes. Okay. So today I'm going to talk about what is wave turbulence. So which is one of my research fields. I'm not going to tell you anything about my specific research or work in this field, but I hope to use the kind of a 1-hour seminar to tell you what wave turbulence means and what is the historical development of the subject and what are the interesting research questions that people care about in this field. Okay, so to begin with, I'm going to start from some motivating question that is familiar to most of us as marine engineers. That is something that we deal with probably in our everyday research about ocean waves. More specifically, here I'm talking about the ocean surface gravity waves. So here I show you 4 pictures I downloaded online about different wave fields in the ocean. Some are from the real photograph, and some are from computer animations, and some are from some artwork in Japan. So all of these look very different. So you see that we have something like a pretty smooth field, or we could have something like a breaking wave with white capping or with wave overturning. But the question that I'm going to propose or I'm going to ask here is that whether there exists some common feature for all these wave fields. So this question is a little bit ill-defined because if you look at the individual wave shape of these fields, they are very, very different. So what do I mean by that we can find some common feature? So by common feature, what I really mean is in some statistical sense. So in particular, we can talk about the wave spectrum S of omega. Essentially, this is the energy spectrum which tells us how much energy, I use S symbol here, how much energy is within the frequency of omega. And basically tells us the energy distribution in the frequency space. So over history, there are 2 famous ocean measurement projects, one called John Swap and the other, just one called John Swap. This is probably measured by some other projects, I don't know the name. So what they do is that they measure the ocean surface with either wave probe or some remote sensing technology, and then they get lots of data of the ocean surface. And then they fit these data into some empirical wave spectrum. So they think that this empirical wave spectrum could give us some rough idea on how the wave spectrum behave in the ocean. So now we have the John Swap spectrum and the Pearson-Moskowitz spectrum to represent the ocean wave field that is used a lot in our research. So the difference between the first one and the second one, that John Swap is for limited fetch, so the wind has not blowing for enough time. But Pearson-Moskowitz is for the situation that wind has blown for a long time to form a stationary spectrum. So of course, these spectrum are very different at different locations in the ocean and with different wind forcing. So I just put some drawing here for different type of spectrum. We have different energy and different peak wave period and so on. However, we do have some common feature that we can draw from the spectrum. That is, if we consider the large value of omega, meaning the large value of frequency. because if we consider that, then all these exponential function becomes 1 because we essentially have exponential 0 when omega becomes large. So what remains as a spectral form is basically this omega to the 5 on the denominator. So that basically means for large frequency range, the spectrum exhibits a parallel form of S omega proportional to omega to the minus 5 power. So that is very common for all these probably I should say most of these data fitted spectrum from the ocean. So there's no theory about it. If you think about this, this is something we completely get from the nature about this parallel range of omega to the minus 5. So in terms of this spectrum, it basically means that if you look at the tail part of the spectrum, they all decay in a particular slope that is a minus 5 exponent. So this is a very common feature that we can find for the surface gravity waves in the ocean. In fact, not only for surface gravity waves, if we look at other wave systems in ocean, we also have similar feature. So here I just show you a figure to represent a very complicated ocean wave field, and you have waves that are generated from very different mechanisms. And I give you 2 examples here. The first one is internal gravity waves. So if you think about surface gravity waves to be generated on the ocean surface where you have air on top and water on the bottom, so you have a very large density gradient on the surface, then in the interior of the ocean, you sort of have a similar situation because your water is stratified. So your density changes when you go down to the ocean. So you have also have a density gradient in the interior of the ocean that can support internal gravity waves. So they transfer sort of in the interior of the ocean. So for the internal gravity waves, people did similar things as surface gravity waves. So basically they measure the data in the ocean and they try to fit the spectrum. So that is what is called Garrett-Monk spectrum today, also obtained from the fitting of the ocean data. And this spectrum also have a parallel form of omega to the minus 2 in some range of the spectrum. And if we think about capillary waves, which are the shorter waves on the ocean surface, essentially on the surface, you have gravity waves that are longer and the restoring force is gravity. And you have capillary waves at smaller scales where the restoring force is surface tension. And capillary wave also has a parallel form with exponent about minus 3.2. Okay, I just, you can say minus 3, that's fine, but I just want to make it more precise here. It's minus 3.2. Okay, not only for ocean waves, and this phenomenon also exists broadly for dispersive wave systems. And here I give you more examples about acoustic waves. And you could also have an elastic plate vibration where you can measure the elastic waves on the plate. It also has a parallel form. And it also applies to gravitational waves that were just detected a few years ago by the LIGO device. And there are a long list here, which I didn't put here. So the question here is that all these things behave like a parallel spectrum at some range of the spectrum. So why is this the case? And in the following, I'm going to try to explain why. And I'm going to do that from 3 hints. And by each hint, I'm going to review some work of some, I would say, giant master in the history of the science development. And from the 3 hints, and at the end, I hope that we'll understand why we have a parallel spectrum for different dispersive wave systems. Okay, the first person, okay, before that, I want to talk about something else. Okay, so can linear wave theory explain this? Because linear wave theory is familiar to most of us who took a class of marine dynamics and that kind of class. So we all talk about linear wave theory. So can linear wave theory explain the parallel spectrum? So what linear wave theory does is basically to say that I have an irregular ocean surface that results from the summation of lots of linear wave modes. So I have linear wave sinusoidal modes with different frequency and different direction and different amplitudes. And after I sum all over these modes, then I get irregular wave surface that looks like the ocean surface. So the problem of linear wave theory is that these modes are pretty much set, meaning that they do not talk to each other to transfer energy between each other. So what I give as the initial condition for these wave modes it will stay like that. It just transported by the dispersive velocity for each mole. And that also means the spectrum represented by the linear wave theory will not change because there is no change of energy between different frequencies. So here as a linear wave do not interact with each other. And that basically means each Fourier mode stays with the same amplitude after created by wind. So whatever wind creates, it will stay like this forever in the linear regime. But the problem is that wind is also not smart enough to manipulate the wave modes into a parallel fall. So I know that by seeing this a little bit hand waving, but this is indeed the truth, that that wind only generates wave usually in a narrow frequency range. It does not support a broad range parallel spectrum. So the linear wave theory that we are most familiar with cannot explain the parallel that we observe in these ocean waves. So we need to interact with each other. That requires us to go to the nonlinear regime. Okay, so how to go to the nonlinear regime? And I'm going to now explain 3 hints from the work from 3 giants in the history of science. And the first one is Kolmogorov. Probably you have come across his work at some point in your field, but if not, I took this introduction from Wikipedia. Andrei Kolmogorov was a Soviet mathematician who made significant contributions to mathematics of a lot of fields. And among these lots of fields, what we are going to talk about is this turbulence. And of course, Kolmogorov is much broader than turbulence, and he has made lots of seminal contributions to different fields of science and mathematics. Here, I would like to quote someone, Jacob Wolfowitz, who is a famous statistician in the US. So over a long period of time, the Cold War, there is no science communication between the Soviet Union and the US. And when later US scientists are allowed to visit Soviet Union, Jacob Wolfowitz, who obviously read lots of work from Kolmogorov about probability theory, and he said Kolmogorov could not possibly be an individual. He must have been an institution. And the reason for me to visit the Soviet Union is to make sure which one is correct. So I just want to quote this to say that he's a very broad person in science and mathematics. Okay, so what did Kolmogorov do for the turbulence? So I put some simple picture here to explain the idea. So Kolmogorov basically said the turbulent flow is all about interaction among vortices of different scales. If I consider water in a barrel and then I stir the water with some stick, so this stirring motion will generate some large vortices in the rotation pattern in the barrel. And then what happens is basically large vortices will generate smaller vortices like what is shown in this animation. So we have large vortices here, and then due to some nonlinear effect, we keep generating smaller vortices. And also show this kind of behavior in the jet flow where we have large structure coexistent with a very small structure. So we have the coexistence of structures of very different scales. And on a higher abstract level, what Kolmogorov said is basically there is an energy cascade process in turbulent flow. So we have some stirring motion, so at large scale to form the injection range where we have lots of large vortices. And then the large vortice has an energy cascade process. It passes energy to smaller scales to generate smaller vortices, and eventually the energy gets dissipated at the small scale of the turbulent flow field. And this process is especially self-similar in the middle range, which we call inertial range. And because of this, Kolmogorov can do some dimensional analysis argument to say that in this range, my power spectrum E of a wave number K, where K as a wave number that is defined as 1 over the scale. So when we have a small scale, we have large K. When we have a large scale, we have small K. So in the middle, what we call inertial range, it satisfies the power law solution argued by dimensional analysis, and this number is minus 5/3 for a turbulent flow. So this is the first hint that we see something similar in a turbulent flow as for a wave field. But the problem is that Kolmogorov's theory is not an analytical solution, meaning that he got this solution purely from some dimensional argument. There's no mathematical theory, no advanced mathematical theory behind this. And we want to do a little bit better than this. And the second one, this is essentially energy cascade about vortices. But for wave field, vortices is not the major components. So the question is whether do we have a similar cascade process for waves? And to answer part of these two questions, I'm going to bring up the second hint about Klaus Hasselmann. So basically, Klaus Hasselmann will tell us if we are in a nonlinear regime of ocean waves, how do they talk to each other and how do we exchange energy among each other? So Hasselmann, some fact about Hasselmann, he got the Nobel Prize in Physics 2021 at the age of 90. And this is a quote for the physical modeling of the Earth's climate, quantifying variability and reliably predicting global warming. So, so this contribution is not directly related to his work in ocean waves, but as I will show you in the next slide, his work in the climate science is closely related and very inspired by his previous work in the ocean waves. And he's a founding director of the Max Planck Institute for Meteorology, which is sort of a major institute for meteorology in German and also, I think, over the world. And his wife, of course, last name is Hasselmann, is also a geophysicist. You will see lots of paper about Hasselmann. So that's some interesting fact about him. So Hasselmann's research is also very broad. Probably not as broad as Kolmogorov, but it's also impressive. So I read something from a review article of Hasselmann's work. So this is what they said. So they basically said people try to understand what Hasselmann works on, and it is like the parable story of blind people trying to understand an elephant. So each of these blind people basically touch one part of the elephant. Some touch the trunk, some touch the side, and some touch the tail. And all of them think that they understand the elephant, but they only understand one part of it. And Hasselmann is an elephant. So, okay, so what does Hasselmann do for ocean waves? As I told you briefly, he basically derived the equation that tells us how waves talk to each other, which is called the wave kinetic equation, which I wrote here. So this equation is actually much more complicated than what I wrote because there is an interaction coefficient that probably will, if I write that down, that could be 1 page of. So anyway, so this equation tells us the time evolution of what is called NK. So NK precisely it is a wave action spectrum, but I will not describe in detail what's the difference between wave action and wave energy. So you could think about NK as an energy wave energy spectrum. So this equation basically tells us if the waves are talking to each other in the nonlinear region, how does the spectrum change with time? So that is a partial NK, partial T term, and it's described by the integral on the right-hand side. So this kinetic equation is sort of the first kinetic equation for wave that appeared in a JFM paper about 1961, and you see that at that time Hasselmann is with the Institute for Naval Architecture, which is similar to us. Okay, so so now I also told you that Hasselmann's climate work is closely related to this wave kinetic equation, and I would like to show you his Nobel Prize speech, and you will see that in the first 5 minutes of the speech, he's actually talking about this equation of his work. So he has a pretty strong accent. So I do not understand everything. Probably you can understand better because your English is better. But anyway, let's listen to it, and I will try to interpret it after from my perspective after that.
Is it not going forward? Oh, video.
Yes, it's a video.
Yeah, linked videos and PowerPoint are always very hit or miss. If it doesn't work, you might be able to click the three dots and open in your web browser.
I think if it's YouTube, you have
That
to
looks
click
like
on it.
Yeah, that looks like a YouTube video. So maybe.
Yeah, it's a YouTube video. Maybe I could go to
Yeah.
Yeah.
Yeah. It's next frontier. Automatically playing YouTube video and Google Slides.
My embedded videos, the bane of my existence. It's always something.
I
Yeah.
integrate YouTube videos in my Google Slides.
We'll get
Yeah,
there.
so-
The full screen.
No sound.
3 minutes.
Oh, so that adapter may not do something. I think we can. Can you pop them over the video? On the side. Send there.
That's fine. I can tell you what he said.
Okay.
You can put on
You can watch
You can
it.
put on the closed captioning or something.
Yeah.
Yeah, in German.
Okay. There's no. Okay, maybe I could show you the pictures. Okay, so this is where he started to talk about it, and basically started from this with kinetic equation. You see some wave spectrum here. So essentially, he's saying that previously people do not understand this nonlinear effect. When people try to understand how spectrum evolves, they usually just put a wind forcing and a dissipation mechanism. So there is only a pumping energy mechanism and dissipation energy mechanism. There is no mechanism of energy transfer from one scale to another in ocean wave field. And what his contribution is actually the development of this equation, which tells us how the wave energy is transferred among different modes. And if you look at today's wave modeling kind of computer code, there's WaveWatch 3 and there's SWAN, and all they implement is actually this thing, this term as a nonlinear energy transfer in the ocean wave field. And then Hasselmann talked about that. Then he applied this technique to sort of other systems like plasma waves and I do not quite remember, but some other wave fields. But essentially, before his climate science work, he really works on this wave kinetic equation, or really works on ocean waves. And then when he go to the climate science work, actually his contribution is exactly related to the wave equation. If you think about this wave kinetic equation, it basically means that we have small oscillations of the individual wave resulting in the change of the spectrum. And his climate science work is basically saying that weather fluctuation changes the global temperature that results in the global warming. So it's closely related by the experience of working on this wave kinetic equation. And I put some note from Hasselmann here. It was really an eye-opener to realize how specialized we are in our fields, and that we need to know much more about what was going on in other fields. Through this experience, I became interested in particle physics and quantum field theory. So I entered quantum field theory through the back door, through working with real waves rather than particles. So I don't know much about quantum field theory, but I know that the methodology about the derivation of this equation is closely related to what people do in quantum field theory. And that is also what Hasselmann found out in his career. Yes.
Is Hasselmann 90 in that YouTube video? Did you say he got his Nobel Prize at 90?
No, last year. No, not that, 21.
No, when he was 90 years old?
Yeah, he was 90 years old at that time.
That's what we're all aiming for, is to be talking like that when we're 90, so it's the goal.
Got 9 more years.
Okay, so now we have this equation which tells us how waves interact with each other, but how that is related to the parallel solution in the waves. So now we need to bring up the third thing about Vladimir Zakharov. And he got a direct medal in 2003 due to his work in wave turbulence. And you are probably less familiar with direct medal, but direct medal is actually the highest honor in theoretical physics. So here is a quote: "For distinct contribution to the theory of turbulence, particularly the exact results and the prediction of inverse cascades, and for identifying classes of turbulence problem for which in-depth understanding has been achieved." So something about Zakharov, and when he was young, not that young, he was expelled from the Moscow Energy Institute, which is his first university due to a fist fight. So what happened is that he had some eye problems, and some students probably make fun of him, and that resulted in a fist fight, and he was expelled. And then later, his talent was found by someone whose name is Rod Sandy. So he took Zakharov as a student, and that's how Zakharov started his scientific career. So this Sandy guy is the first student of Lev Landau, who is a giant in physics in the world. It's kind of in a parallel position as Richard Feynman. And Zakharov's research is also very broad, and he also like another thing, writing poem. And here, this is a book of his poem. It's called Paradise for Clouds. I never read it, but it's on Amazon. The review is pretty good as I saw it, but I don't know if those reviews are written by his students or. Okay, so I can tell you another story about Zakharov. So there's a postdoc in the math department whose name is Chris DeCenter. He just arrived at the university last year, and his undergraduate is in Arizona, University of Arizona, where Zakharov teaches. And at that time, he doesn't know why Zakharov is famous or something, and he just took a class with Zakharov. And that class is about differential geometry and general relativity. So which is a little bit unbelievable that he knows things from a very different field. Okay, so what did Zakharov do? Basically, Zakharov took the kinetic equation derived by Hasselmann, and Zakharov said that there is an exact solution to this kinetic equation. So what do I mean by exact solution is that if I make my left-hand side term equal to 0, meaning that I assume a stationary spectrum that does not evolve in time, then I solve the equation of the right-hand side being equal to 0, and then I can find the exact solution for my wave spectrum nk. And if we do that, we essentially get nk of an analytical solution of a constant c. This constant c is called Kolmogorov constant times energy flux p, where p basically transfers energy from large scale to small scale, and this p tells us the rate of energy transfer to some power of alpha, and then we remember k to some power of beta. So this alpha and beta are different for different wave systems. Essentially, for any dispersive waves, you have a methodology that you can form the wave kinetic equation first, and then you can derive this solution based on the Zakharov's technique. And what this basically tells us is as follows. In the wave field, we also have a wave energy cascade process where we have the energy injection to form the long waves, and the long wave pass energy to short waves from this energy flux process described by P, and then the energy dissipates at short waves by the viscous effect. So that if you look at the energy spectrum, it looks pretty similar to what happens in the turbulent flow. We have some inertial range where the analytical solution exists. It looks like C times P to the power of alpha and K to the power of beta that can be derived for different wave systems. And the first sort of solution for this type is discovered by acoustics with Zakharov was a PhD student in 1964. And then his PhD thesis includes the theory of surface grabbed waves that gives us a polar solution of omega to the -5 that is consistent with the Pearson-Mascovitch spectrum and John-Swab spectrum. But now this is obtained directly from the theory. So of course, later he generalized this process for many different wave systems, and it becomes sort of a methodology. Okay, so this is the historical development, and I'm also going to tell you a little bit about what people in this field are working on these days. So essentially, it seems that the development is complete. We have an ideal solution that agrees to the theory, but actually, the research and the story is far from complete. There are so many open questions there, and now we have so that now we have a Simon's collaboration on wave turbulence, which gathers lots of scientists in this field to study this thing together. So I officially joined this group this year as one PI and funded by the Simons Foundation for the next 3 years to work on wave turbulence. So there are 3 types of person in this collaboration. One is mathematicians, and second theoretical physicists, and third one experimental physicists. So I think I belong to the second group, but I also work a little bit on mathematics these days, not too much because it's hard for me. Okay, so what does people do? Like each group of people do. So for mathematicians, I used to say that in my class that mathematicians are animals from a different world. They are considering things that probably seems boring for us or seems not useful at all, but it's anyway pretty deep. And I would like to tell you what mathematicians are working on for wave turbulence. And the first thing they are interested in is the rigorous derivation of the kinetic equation. The previous derivation by Hasselmann and also later generalized by Zakharov is not rigorous. They call it a physicist derivation. They need to make certain assumptions. Some of them are not very realistic for the derivation. For example, if you know turbulent flow, there is something called a turbulent closure model. You need to place there to close the model and do the derivation. So mathematicians want to get rid of all those kind of things. And they are basically saying that if I'm given an initial field of random waves, can I directly derive this equation? And they have made significant progress in this field. Actually, one important person in this is Professor Zakharov in the math department. And they are now able to derive this equation and justify that this equation is valid for a pretty long time window. And the second thing they are interested in is the well-posedness of various PDEs. So basically, as physicists, if we are given a PDE to govern a physical phenomenon, we think about, okay, we do simulations and we look at how things behave and we understand the physical phenomenon. But mathematicians are different. So when they are given a PDE, the first thing they want to think about is whether this PDE, the partial differential equation, is well posed or not. Essentially, it basically means that if I'm given a initial condition, how long can I prove that the solution exists? It does not blow up, go to infinity or something. If I can prove that this solution exists for a certain period of time, then I have something called local well-posedness. And if I can prove this solution exists for infinite time, then I have the global well-posedness of the PDE. And the holy grail for this field, I think, is the well-posedness of the Navier-Stokes equation. For now, nobody can do that. And if you can do that, you get $1 million as a prize. But nobody has been close to that for now. And they are also interested in the stability of the solution. So how, if I'm given a solution, how do I understand its growth in time, sort of thing. And for physicists, what we do is basically apply wave turbulence for various different wave systems. Basically, the methodology established by Zakharov. So for example, now there is an application to gravitational waves and application to FPU, maybe I should say FPUT system, that is something discussed by Fermi and his colleagues about mass and spring chain that system that they could not give a theoretical they could not have an understanding at that time. But now with wave turbulence theory, we have a much better understanding of the problem. And we are also interested in the volatility range of the wave turbulence theory. Essentially, we have this kinetic equation, and at what situation is it valid, and at what situation it is not valid. So that involves lots of details. And if you want to know more about this, I would encourage you to talk about my students, Alex, Ashley, and Joe. And also for various wave systems, there is another focus today is about the internal gravity waves, and Sensia is working on that. Okay, so I'm going to tell you a little bit about what experimental physicists are doing, which is more interesting, I think. Okay, so this is something appeared in annual review of fluid mechanics paper. Basically, this some wave tank where we do experiments to observe the Kolmogorov-Zakharov spectrum. You see that they are all with different shapes and with different wave generation mechanisms. Some of them have a pedal to oscillate, and some of them they essentially oscillate the whole tank altogether to generate waves. And they also have different measurement device with a probe or with cameras to measure closed surface. And they try to observe parallel spectrum from these experiments, and they did observe things that is close to the theory. And you could think about someday to do some experiments like this in the MHL. I think it's doable. Okay, so what they observe actually are parallel spectra with two different segments, and each segment are with different slopes. And the reason for this is because for surface waves, at long surface waves dominated by gravity, the restoring force is gravity. And at smaller scales, the physics changes and it's dominated by the surface tension. So from low frequency to high frequency, the physics transits from surface gravity waves to capillary waves. And as you have seen that we have different parallel range for these two types of waves, so that we have two segments of the spectrum. But experimentalists are not satisfied with this because with this spectrum, they have a long range of transition. It's kind of hard to get each slope very precisely. So they are thinking about how do I get each part of the spectrum longer than what they can do in these kind of experiments. So that comes this this slide. First of all, how I can get a capillary wave spectrum that is very long. And the way to do that is to get rid of gravity. And there are two ways to do it. One is called a parabolic flight. So what they do is that they have a plane that make a maneuver like a parabola. So if they do that, it basically means that I'm following a free fall of my plane, meaning that I have a zero gravity environment where I can do this experiment. So they only have about 22 seconds to do the experiments at this time window. And the second thing, they go to International Space Station to do the experiments. So by doing that, they get a very long range of capillary wave spectrum that actually agrees with the theory very well. So you see that these exponents, it's 3.1, and previously I said 3.2 because the theory is closer to 3.2. Okay, and they can also do a high gravity experiment. So what they do is that they put a spinning device, and in the spinning device, the effective and they have a wave container here. The effective gravity in this case would be the total force of the true gravity plus the centrifugal force. So if the spinning is fast enough and this force is large enough, I can have a very large effective gravity that overcomes the surface tension on the longer range. So then they can observe a very long range of parallel spectrum in the gravity wave range. And the last thing I'm going to show you is about some experiments with our ocean as a test bed. That is a field measurement of internal gravity waves. So here, what I put is basically the measurement of internal gravity waves at many different locations in the ocean. And you see the common feature that we have a long range of parallel solution for all these measurements, and which it sort of agrees with the theory. But for internal gravity waves, actually there are more mechanisms are the situation is more complicated. So the kinetic equation is probably not enough to describe everything, and also we have some ill-behaved solution in certain cases. So if you want to know more about internal gravity waves, I encourage you to talk to Cynthia. So she's the one who works on this project. Okay, that is everything I hope to tell you today. Thank you very much. But before the question session, I would like to make an announcement or maybe advertisement. So if I'm again invited to give a talk next year at this time, I'm going to choose one of these two topics. The first topic, I'm going to tell you who is Walter Munk. You have seen the name Munk in the Garrett-Munk spectrum, which bears his name. But he's also, he does a lot of things about ocean, and he's named the Einstein of the ocean by the New York Times when he passed away about 2 years ago at the age of 100. So I'm going to tell you what Walter Munk does. And the second possibility that I would like to talk about the three-body problem. There's a novel, Chinese novel about three-body problem, but I'm not going to talk about that. I'm going to talk about three-body problem as a scientific problem, how people's understanding evolved over history on this problem. And surprisingly, or probably not very surprisingly, one climax of understanding of the three-body problem is also related to Kolmogorov in terms of so-called KAM theory. So I can talk about one of these topics later, next year. Thank you very much. Yes, Nani?
So I know Navier-Stokes. I don't know the quantum version. So what's the relationship? Because I think does it generalize the older differential PDEs, and we don't need those? The special cases of these new ones.
You are talking about what's the relation between
the new nonlinear wave equations and the older, textbook Navier-Stokes that.
The relation between, so I try to understand the relation between Navier-Stokes and wave equations. Okay, they are pretty different. So this solution by Kolmogorov. So for waves, we have this methodology by Zakharov to derive the Power spectrum. But this original solution by Kolmogorov, still we do not have very good technique to do it. And the one person who did this over his career is Robert Krashen, who also got the Dirac medal together with Zakharov. He's able to derive this, but with some strong assumptions that might not be correct for Navier-Stokes equation. And the key difference between Navier-Stokes equation and the wave equation, there are two differences. So one is that wave equation is dispersive, meaning that I have a dispersion relation. Longer wave traveled with different velocity at shorter wave. But for Navier-Stokes equation, there is no dispersion. So that mechanism is lacking. And the other difference is that for all these wave systems, we can assume that the nonlinearity is not very high, meaning that basically the nonlinear term in the equation is much smaller than the other term. So I can apply some perturbation theory to deal with the nonlinear term. That is only valid for waves, but not valid for Navier-Stokes equation. So that is another reason that this wave turbulence theory is also called weak turbulence theory, because I need my nonlinear term to be not large enough. But for Navier-Stokes equation, if you think about the nonlinear term as the inertial term in the equation, it can become very large depending on Reynolds number and things like that. So essentially, this kind of theory does not apply to the Navier-Stokes equation directly. So I think there is a group of people working on the Navier-Stokes equation in Europe these days. They apply something called a non-perturbative renormalization technique that is borrowed from the quantum field theory. They are trying to do it, but I don't know much about that. Yeah, I just know they are working on this.
There's an ongoing work to connecting.
It's ongoing
these
work.
two models.
Yes, I think.
So the science is just fantastic and amazing. So can you tell some of the engineering aspect or
Sure,
the connection with the engineering?
I can think about the first connection to the engineering field is just this kinetic this kinetic equation here is closely related to the wave modeling problem. So now nowadays we do global wave modeling to guide the shape routing and kind of thing by NOAA and by IFRIMER which is the weather agency in Europe. So what they do is basically a simulation of this equation plus some forcing and the dissipation terms. And by doing that, they can have the next 3-day forecast of the ocean wave field to guide the engineering application. So that is one thing. Other things, I don't know. I just think broadly, if we have a ship excited by spectrum, do we also have the parallel thing that we can explore for that? I don't know. I have never done anything for that. Another thing about I can point out about connection between the science and engineering is actually the internal gravity wave. So the internal gravity waves, because these days we do climate modeling, we do global ocean models, and the grape size is very large for those models. So we cannot capture the internal gravity waves. So in other words, the internal gravity waves needs to be parameterized for those models to try to give us a reasonable understanding of how the global ocean or global climate changes. And so that relies on a good understanding of the theory of internal gravity waves. So you know that the global ocean model kind of thing is also of interest to engineers and I think to policymakers to deal with the climate change problem. Yeah, Ash.
In your slide on internal gravity waves,
yeah,
the spectra had a peak, and then there was a hard wall.
Right.
What determines that?
Right. So
that length scale or time scale.
Yeah. So this peak is basically the forcing of the ocean that comes from either the tidal forcing or the wind forcing. So the wind forcing sort of goes like as a inertial frequency that is sort of the rotation frequency of Earth, and then the tidal forcing is a little bit higher than the inertial forcing for some kind of tide. So usually you see either one peak, so probably there's tidal is maybe tidal is not very strong, or you see two peaks, one from the inertial frequency of wind and the other from the tidal forcing. So it's based on the forcing mechanism. Yes.
So I'm curious to hear, in your own work, is there a particular recent finding or direction that you're really excited to follow up on?
I can
just briefly.
Okay, I'll tell you what Joe is working on. So of course I think Joe, Alex, Ashley, and Cynthia, they are all working on very interesting problem. But what Joe is working on is basically to revisit the Hasselmann equation to see whether this is correct or not. So we have seen in some cases that this equation is not very accurate. So it might be beneficial to add another term to this equation to make this more accurate. So we are still in the exploration stage, but we think that this equation can be made better to explain ocean waves. Yes, David.
So two things. First, the nonlinear interaction is primarily hydrodynamic, right?
Yes. Different waves have some okay.
No, for the ocean waves.
Yes.
Okay, so that's where the nonlinear comes. The other thing is you didn't say much about viscosity. Right. Usually all these spectra eventually at some point viscosity takes over at the very highest wave number. So
yes. So essentially for waves, viscosity of course it's there to dissipate energy, but the major mechanism for energy dissipation in at least for surface gravity waves is wave breaking. So at smaller scales you have the white capping thing, the wave becomes steeper in terms of amplitude times the wave number. So it breaks, and that dissipates more energy than viscosity. So viscosity also it's not in the non-breaking case. Maybe you have a regular wave. That viscosity is important, but in the spectrum case, it's more like the dissipation by the.
Well, that's certainly true in the gravity range, but in capillary range, wouldn't the viscosity winds up being more important, right?
Yes. So that's why we don't have very long range of the spectrum for capillary wave if we don't do special techniques. So this competing between the viscosity and the nonlinear transfer effect is similar as Reynolds number in the turbulence. So for this one, for Navier-Stokes equation, it's just set, but for this one, you have different mechanism that is not described by the equation. So you need to kind of get a balance between these two. Yes.
In your slide on recent, you had math, there was theoretical physics, and then there was experiments. Yeah.
Yes.
I was wondering what your thoughts were on large-scale simulation and its potential to maybe look at this problem.
Yeah.
Or aspects of it.
I think that is very important. So, for example, there is a unsolved problem for surface gravity waves. So, essentially, over the history, there are two types of spectrums. One is called the KZ, Zakharov spectrum, which is what I described today. And the other one is actually they call the Phillips spectrum, originated from O.M. Phillips. And the Phillips spectrum basically says if my wave steepness is very large, I have white capping, I have breaking at all scales, I can form a different spectrum than Zakharov, Kolmogorov spectrum. So that thing, I think nobody has understood it, and it will benefit a lot if we have a simulation. We have a simulation to sort of simulate what happens at a large wave steepness, because the simulation, traditional simulation for surface gravity waves is based on the potential fluid. You cannot really capture those white capping thing, so there's no chance that you can understand it from here. So if there's an LES or DNS, probably too small range, but LES simulation to simulate this thing, I think it can advance our understanding a lot. And the other thing is about the global ocean model that I discussed, that is sort of large scale simulation.
Is there also, that's very interesting if you can follow up with you on that, but
Yeah.
Is there also interest in looking at things in the physical time domain, or is basically all the work in
Yeah,
space?
I'm also interested in what happens in physical domain. Especially in the physical domain, we have some inhomogeneity of, I don't know, for surface gravity waves, if we have some non-uniform current that varies with space, how does it interact with the spectrum? Those kind of things has not been done. But I think it's very interesting to look at those problems. Thank you. Yes, Chigang.
Yeah. Anybody or any figures from the University of Michigan have made a significant contribution to the field historically in the past 100 years or something like that?
I think okay, I can describe two big contribution in the mathematicians' work. One is what I mentioned by Zakharov, who is a professor in the math department. He's able to derive the rigorous derivation of the wave kinetic equation for a pretty long time scale. It's maybe 100, more than 100 pages of paper I never read through. Okay, so he's able to derive this equation. That is a major achievement for the field. And the second one is also some in the math part. It's Professor Sijue Wu from the math department. So that is related to the well-posedness of PD. And Professor Wu actually she proved that the surface gravity wave equation is globally well-posed if I have a real number domain. So that is the first global well-posed result for surface gravity waves. It basically means that for surface gravity waves equation, this set of PD if I'm given a initial condition, I know that exactly over infinitely long time, this solution does not blow up. Or something. That is sort of the second big achievement among these mathematicians' work. For physicists, I think probably I'm the only one who work on this in this field in our university, and now plus my students. So I hope there could be a big contribution from us.
Yeah, nice. Thank you.
Yeah, thank you.
Robot related question.
Yeah.
This is for the surface of the ocean. Does that mean the load distribution on ships and surface vehicles is different from
Sorry, what distribution?
the distribution of load force
Oh, load. Okay.
caused by the waves?
Yes.
Is it going to be different the surface than if we go deeper in the ocean, for example, like
If
underwater?
it's caused by surface gravity, it's will be very different because for surface gravity, the motion decays exponentially from the surface to the deeper part of the ocean, so that you have much more fluid motion at the surface compared to deep down. But there are other mechanisms. So if we just consider surface wave, this is what happens.
So one model doesn't work both on the surface and in deeper part of the ocean.
You have a solution for surface gravity wave, which tells you the whole field, how the whole field moves. It's just that on the surface is more variable.
All right, well, I think that this is an excellent first
Thank you, Lisa. Yeah.
first stop for our seminar series. So thank you all. I know.